first step, I'm going to just copy down what's happening in my original system, and I'll call that system number 1. And then that 100-pound force is going to be acting at an angle that's, we can use a ratio triangle at 3, 4, 5 ratio triangle, and we'll have our point A. And I'll use the same coordinate system for both of my systems 1 and 2. All right, so this is my system 1. All I did was copy down what was given. 3 forces, oh, and I need the dimensions here. Now I have everything from my original system down. So the next step is I'll go back just to follow our steps here. Now we draw our equivalent system. So the same object, but now simplified to have only that one force and then either the couple or an unknown distance away from some point. So now we're at step 2. All right, so they tell us they want the equivalent system or the simplified system to have one force and a couple, and it's located at A. So in system 2, at A, I have my force acting. Really what it's going to be is some force acting at some angle from the x-axis, but mathematically, instead of doing it that way to begin with, I'm going to say that that force has some x component, fx, and some y component, fy. Once we find those, then we can go from the Cartesian back to the polar, and we can find the magnitude and direction of that force. But by hand, this is an easier thing to solve, and we'll see in the equations where that comes out. So a force that acts at A with components fx and fy, and because we specified the point at which it acts, we're also going to have a couple acting. I'll draw it at that point, but as I discussed the other day, the location of the couple actually does not matter. But I'll draw it here just so everything's at one place, and I'll call that C. I'm assuming it's counterclockwise, and that will be reflected in the equations, but you could assume clockwise as well, but it's just going to change slightly what the equations are. So it's just easier, I think, if you assume positive directions, and we'll see this once we get into chapter 5, or the second unit. Assume positive and let the math tell you if you're right or wrong. And for most of what we do, I think that's an easier strategy to use. So that's all system 2 is. It's one force that I pre-broke out into component form, and a single couple, and everything's acting at A. All right, so if we look at this picture, I don't know fx, I don't know fy, I don't know c. Now I have to write my equations. I'm not going to, I'll just say that I'm summing forces x, summing forces y. This is not an equilibrium. They are not equal to 0, but they will be equal to each other. So in my equation step, I'll start with equation 1. If I sum all of my forces in the x direction that appear in system 1, again, not equal to 0, I just have to look at the picture and see what I have here. So in the x direction, in picture 1, I have the 150 will not appear in the x direction. All of the 200 appears in the negative x direction. And then the 100 will be only a component of it. So here I have a ratio triangle, but I could have used that angle as well. So not the whole 100, but the 3/5 of 100 will be in this equation. So plus 3/5 times 100. Right, so those are the only 3 forces. And again, the 150 did not appear here. It's only in the y. And 3/5 of the 100 appears. So I get the net force acting on system 1 is going to be a negative 140 pounds. Now do the same thing in system 2. The simplified system is always easier. If I look at all of the forces in system 2 that have a component in the x direction, well, I only have 2 components of a force, but fx is the only thing that has an x component, and all of it is in the x direction. So if I sum forces in the x in system 2, I just get what I'm calling fx. My goal here is for the systems to be equivalent, which means when I sum forces along an axis on one system, it's equal to the sum along that same axis in the second system. So now, the last step is equating these two things. So the net effect was Fx, and from system 1, I got negative 140 pounds. Therefore, Fx must be negative 140 pounds. It's a negative, which what that means is I assumed it was pointing to the right. It's actually pointing to the left, and that will be fixed later. The value right now matches the picture that I drew. Now I do the same thing in the y direction in both systems. Oops, not equal to 0. In system 1, in the y direction, now I have that negative 150. The 200 does not appear here, and in this case I have the 4/5 times 100. That's in the positive y direction. Adding these together, my net force in the y direction in system number 1, I actually also get negative 70, I get. Then system 2, the only thing that has a y component is Fy. Therefore, Fy must be negative 70, since the sum of forces in y in system 1 is equal to the sum of forces in y in system 2. So the y component of that equivalent force has to be negative 70 pounds. So you see that second step, always very easy, and that's by design. We want to simplify the system so there is only a single force in any one direction. I have Fx, I have Fy. The only thing I don't know now is C. What's the couple that should be applied here so that the systems are equivalent? I did the sums of forces. I now have to sum moments together. And that's my last step. So this is where we actually have more of a choice. I used an x right, y up coordinate system, so these equations were already determined for us. What I need to do is I have to sum the moments in system 1. But here's where we get a choice of what point to sum about. Again, it doesn't matter which point we choose as long as it's the same point in both of our systems. So oftentimes what will be easier, at least from system number 2's perspective, is if we were to choose point A in system 1 and system 2, starting at picture 1, what contributes to the moment around A, or how are we going to find the total moment around point A in picture number 1? Right, the 150 will contribute because, again, how do we know the perpendicular distance? We can make a line parallel to the force that passes through the point we want to know the moment about, and then that perpendicular line is what we use as that perpendicular distance. So right, the 150 does contribute to the moment around A. So it's the force, which is 150, times its perpendicular distance to point A, which in this case is 3 feet. And since we're operating in 2D, if I'm using the scalar approach, I need to include, is this going to be a positive or a negative moment around point A? So will the 150 be a positive or negative? Right. Negative because it creates a clockwise spin around A. So clockwise is negative. That's just the moment contribution from the 150. We now have to look at the other forces. Going along, what's the moment contribution due to the 200-pound force? That's 0. Its line of action passes through A, so we got off easy there. And lastly, this 100-pound force, it's not all in X, it's not all in Y. If we remember back to when we were looking at the 2D moments, what we can do that's going to be easier is if we look at what's the contribution due to its horizontal component and the contribution due to its vertical component. That's going to make it easier to calculate. So let's just look at its horizontal component first. We know that the force of the horizontal component is 3/5 times 100. That's the force, but now what's the perpendicular distance from the horizontal component to point A? Right, 6 or 4 from the horizontal component here. Right, it's going to be the 4, because again, We want the line that's parallel and passes through A. That distance is the 4 feet. So for the horizontal component, we multiply that by 4. And does the horizontal component create a clockwise or counterclockwise moment around point A? Right, also clockwise, so also negative. Finally, the vertical component of the 100-pound force is going to be 4/5 times 100. Its moment arm, or its perpendicular distance, again, drawing that parallel line through A, that is my perpendicular distance with respect to the vertical component of the 100 pounds. That is 6 feet. And does the vertical component create positive or negative moment around A? That is positive because it is going to be counterclockwise around point A. So we had 3 forces, but we did have to, this was 0. We accounted for this one. This one I split into 2 forces, a horizontal component and a vertical component. If we add all of this together, we're going to get that the net moment around point A is negative 210 pound-feet. Now, taking the sum of moments around A was a hassle for picture number 1, but this is where we benefit in picture number 2, because by taking the sum of moments around A, Fx goes away, or the contribution due to Fx goes away, the contribution due to Fy goes away, so we're left with just C. And by design, Fx, Fy are not in this equation, so that means to equate MA1 and MA2, this must be equal to negative 210 pound-feet. Right, so we assumed counterclockwise just because mathematically it's easier because then I can just write C here. It turned out that assumption was wrong, which is okay as long as we're aware of that issue. We have Fx, we have Fy, we have C. Now we can draw our equivalent system. In this case, I want to express it as in polar form because, again, if we have some actuator, we need to know at what angle should it be acting and with what force should it be acting. And we also have this twisting here that we want to apply in the correct direction. So in this case, I'll actually redraw figure 2 to reflect the correct angles here. So it turns out that the force has a negative x component and a negative y component. So it's actually pointing into quadrant 3, if drawn correctly. And the couple was negative when we drew it counterclockwise. So this is the actual correct direction of the couple with 210 pound-feet. I want to find the angle it makes with the x-axis, and I want to find its magnitude. And this goes back to what we talked about in chapter 2 when we were just adding vectors together. So I have its components, now I need to find its magnitude. So what will the magnitude of F be? Or how do we find it? Right, square root of the sum of the squares of its components. So the square root of 70 squared plus 140 squared means that this force will have a magnitude of 157 pounds. And I want to find the angle it makes as measured counterclockwise from the x-axis, which I'll call theta here. But remember, because we're in quadrant 3, we have to be a little bit careful with how we're finding this. So if I draw just a little triangle here to help us out, I can find that distance easily because I know that the vertical leg is the value of Fy is 70. And I know the horizontal leg has a value of 140. So I can find this, I'll just call it alpha here. I can use inverse tangent of opposite over adjacent. That's 70 over 140, which is 1/2. So that value alpha is 27 degrees. Right, so I don't want to take it from 180 because if I go this amount alpha, I then have to go 180 degrees more to get to the x-axis. So because I'm in quadrant 3, I add 180 to this to get the value of theta. So this 27 plus 180 is going to give me 207 degrees as measured from the positive x-axis.